The morning of May 8, 1945, in a field outside the Belgian town of Mons, 3 American tank crewmen from the 3rd Armoured Division stood in front of a machine that should not have existed. They had heard the stories. Every tanker in the European theatre had heard the stories. The German Tiger tanks were supposed to be the most fearsome armoured vehicles ever built, mechanical monsters that could destroy a Sherman from 2,000 yards away, while American shells bounced harmlessly off their thick armour. But this was not a Tiger. This was something else entirely. The tank before them was massive, larger than any armoured vehicle they had ever seen. Its hull alone was longer than their Sherman by more than 3 feet. The turret, angular and imposing, looked like it had been carved from a single block of steel. The gun barrel extended forward like the arm of a crane, impossibly long, impossibly thick. This was a Panzerkampfwagen Tiger Ausführung B, what the Germans called the Königstiger. The Allies called it the Tiger II, or sometimes the King Tiger. The 3 Americans, Staff Sergeant Robert Early, Corporal James Mitchell, and Private First Class Tom Henderson, had been ordered to examine the abandoned tank and determine if it could be moved to a collection point for technical intelligence evaluation. They approached carefully, even though the war in Europe had ended the previous day. Old habits of caution died hard. The tank showed no obvious battle damage. There were no penetration holes in the armour, no blown tracks, no signs of fire. It simply sat there, silent and massive, its engine cold. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Sergeant Early climbed onto the rear deck first, finding the engine access panels. He pried one open and peered inside. The Maybach engine was intact, no obvious mechanical failure. He moved forward to the turret and pulled himself up. The commander's cupola hatch was unlocked. He opened it and looked down into the fighting compartment. Everything appeared in order. Ammunition racks were partially full. The gun breech was clean. Radio equipment was still in place. The crew had simply abandoned it. Mitchell and Henderson joined him on the hull. They examined the exterior, walking around the massive vehicle, taking measurements with a cloth tape one of them carried. The armour was extraordinarily thick. The frontal hull plate appeared to be at least 6 inches thick, perhaps more. The turret front was even thicker. They had never seen armour like this on any tank, German or American. But it was Henderson, the youngest of the 3, who noticed something odd. He had climbed into the turret to examine the gun controls and the traverse mechanism. He called up to Early. "Sergeant, there's something wrong with the turret traverse. I can't move it." Early dropped down into the commander's position. He located the manual traverse wheel, a large hand wheel connected to a gear system that should allow the crew to rotate the turret by hand if the powered system failed. He tried to turn it. It moved, but with tremendous resistance. He put his full weight into it, gripping the wheel with both hands and pushing. The turret moved perhaps 2 degrees. Then it stopped, the resistance too great to overcome. This made no sense. Every tank had a manual traverse backup system. The Sherman could traverse its turret by hand. It was exhausting work, requiring about 90 turns of the hand crank to rotate the turret a full 360 degrees. But it could be done. A trained crew could manage a full rotation in about 2 minutes of hard work, but this Tiger II turret barely moved at all under manual power. Mitchell, who had some mechanical aptitude, examined the traverse mechanism more carefully. He traced the linkages from the hand wheel to the turret ring. Then he found the hydraulic traverse motor and the associated pumps and fluid reservoirs. He studied the system for several minutes before he understood what he was looking at. The Tiger II represented the absolute pinnacle of German tank design philosophy, as it had evolved through the first 5 years of the Second World War. To understand why this particular tank existed in this particular form, one must understand how the Wehrmacht had come to believe that bigger, heavier, and more heavily armed and armoured was always better. In 1939, when Germany invaded Poland, the Panzer III and Panzer IV tanks were adequate machines for their time. The Panzer III mounted a 37mm gun and had armour ranging from 15 to 30mm thick. The Panzer IV had a short-barreled 75mm gun and slightly thicker armour. These tanks were not meant to fight other tanks primarily. They were meant to support infantry, break through defensive lines, and exploit breakthroughs with speed and shock. But in 1941, when Germany invaded the Soviet Union, Wehrmacht tank crews encountered something completely unexpected. Soviet 34 medium tanks and KV-1 heavy tanks were superior in almost every measurable way to the German tanks opposing them. The 34 had sloped armour that provided better protection than flat plates of greater thickness. It had a powerful 76mm gun. It had wide tracks that gave it excellent mobility in mud and snow. The KV-1 was even more formidable, with armour up to 100mm thick that German anti-tank guns simply could not penetrate. German tank crews reported firing round after round at Soviet tanks and watching their shells bounce off without effect. Meanwhile, Soviet guns destroyed German tanks with single hits. The psychological impact was severe. German tankers, who had considered themselves masters of armoured warfare after victories in Poland, France, and the Balkans, suddenly felt vulnerable and outmatched. The German response was to escalate. If Soviet tanks had thick armour, German tanks needed thicker armour. If Soviet guns were powerful, German guns needed to be more powerful. This philosophy led directly to the development of the Tiger I in 1942. The Tiger I mounted an 88mm gun derived from the famous Flak 18 anti-aircraft gun. It had frontal armour 100mm thick. It weighed 56 tons, more than twice the weight of earlier German tanks. The Tiger I was formidable in combat. Its gun could destroy any Allied tank at ranges exceeding 2,000 yards. Its armour could resist most Allied anti-tank weapons except at very close range. But it was also mechanically complex, difficult to produce, and required constant maintenance. Only 1,347 Tiger I tanks were built during the entire war, a tiny number compared to the tens of thousands of American Shermans and Soviet 34s. German leadership was undeterred. If the Tiger I was good, a bigger Tiger would be better. Work began on the Tiger II in 1943. The specifications were ambitious to the point of fantasy. The new tank would have armour thick enough to resist any existing Allied gun. It would mount a longer, more powerful version of the 88mm gun, capable of destroying any tank at extreme ranges. It would incorporate every lesson learned from combat on the Eastern and Western fronts. The designers at Henschel and Porsche competed for the contract. Henschel's design was selected for the hull and running gear. Porsche's turret design was initially chosen, though it would later be replaced by Henschel's turret design in production. The resulting tank was a monument to German engineering ambition and industrial determination. The Tiger II that entered production in January 1944 was the heaviest tank to see operational service during the Second World War. It weighed 69.8 tons in combat configuration. For comparison, the American M4 Sherman weighed approximately 33 tons. The Soviet 34 weighed 32 tons. The Tiger II was more than twice as heavy as either of these workhorses of Allied armoured forces. This enormous weight came primarily from armour. The frontal hull armour was 150mm thick, sloped at 50 degrees from vertical. This angle increased the effective thickness to approximately 230mm against a direct hit. The turret front on the Henschel production turret was 180mm thick. The side armour was 80mm. Even the rear armour was 80mm thick. This was armour on a scale that made the tank nearly invulnerable to frontal attack from any Allied tank gun in service in 1944. The main gun was the 88mm KUK 43L71, one of the most powerful tank guns of the entire war. The barrel was 71 calibers long, meaning the barrel length was 71 times the diameter of the bore. This extreme length gave the gun a muzzle velocity of 3,280 feet per second when firing armour-piercing rounds. At 2,000 yards, the gun could penetrate 132 millimeters of vertical armour plate. No Allied tank could survive a direct hit from this weapon at any combat range. The optics were superb. German optical engineering was the finest in the world. The gunner had a binocular telescopic sight with magnification that allowed precise aiming at extreme distances. The commander had a rotating cupola with vision blocks that provided excellent situational awareness. The gun itself had a hydraulic stabilization system that, while not allowing accurate firing while moving, did help in rapidly acquiring targets after the tank stopped. Inside, the Tiger II was relatively spacious by tank standards. The crew of 5 had defined roles. The commander stood in the turret cupola, directing the crew and maintaining awareness of the tactical situation. The gunner sat to the left of the gun, operating the main weapon through electric and hydraulic controls. The loader stood to the right of the gun, handling the 2-piece ammunition. In the hull, the driver sat on the left with the radio operator and hull machine gunner on the right. The engine was a Maybach HL 230P30, a V12 gasoline engine producing 690 horsepower. This sounds impressive until one considers that this engine had to move nearly 70 tons. The power-to-weight ratio was less than 10 horsepower per ton, compared to nearly 16 horsepower per ton for the Sherman. The Tiger II was not a fast tank. Its maximum speed on roads was 25 miles per hour under ideal conditions. Cross-country speed was considerably less, often below 10 miles per hour on rough terrain. But speed was not the point. The Tiger II was designed to engage enemy tanks at extreme ranges, destroying them before they could get close enough to threaten the Tiger. In theory, a well-positioned Tiger II was nearly invincible. Its armor could resist enemy fire. Its gun could destroy enemy tanks at ranges where they could not effectively fight back. German tank doctrine called for Tigers to be used as mobile strongpoints, anchoring defensive positions or supporting attacks by destroying enemy armor from range. The turret traverse system was electric and hydraulic. A generator driven by the main engine produced electrical power that ran hydraulic pumps. These pumps pressurized hydraulic fluid that operated the turret traverse motor. Under power, the turret could rotate 360 degrees in approximately 19 seconds, reasonably fast for such a massive turret. The system was sophisticated and, when functioning properly, effective. There was a manual backup system, as there was on all tanks. A hand wheel connected through reduction gears to the turret ring allowed the crew to traverse the turret manually if the powered system failed. This was standard practice. Tank designers understood that mechanical systems failed, especially in combat when tanks were hit, when engines died, when hydraulic lines were severed by shrapnel. The manual traverse was the last resort, the system that would allow the crew to continue fighting even when everything else had failed. What Mitchell discovered in that abandoned Tiger II outside Mons was a design characteristic that fundamentally compromised the tank's combat effectiveness. The turret of the Tiger II, including the gun, weighed approximately 11 tons on the Henschel production turret. This was not the 25 tons sometimes cited in post-war accounts, but 11 tons was still an extraordinary mass for a tank turret. For comparison, the Sherman's turret weighed approximately 5 tons. The Churchill infantry tank's turret weighed about 6.5 tons. This 11-ton mass had to rotate on a turret ring that was 1,850 millimeters in diameter. The turret ring was the circular opening in the hull roof where the turret sat. It included a ball-bearing race that allowed the turret to rotate smoothly. German engineers had manufactured this ring to very tight tolerances with high-quality bearings. Under powered traverse, with hydraulic pressure driving the traverse motor, the system worked adequately. But the manual traverse system was connected to this same turret ring through a reduction gear system. The hand wheel in the turret was connected through multiple gear reductions to provide mechanical advantage. In theory, this should have allowed the crew to traverse the turret by hand, though slowly and with considerable effort. The gear ratio on the Tiger II's manual traverse was approximately 720 to 1. This meant that 720 complete rotations of the hand wheel would rotate the turret 360 degrees. German engineers had calculated this ratio based on the assumption that 2 crew members, the gunner and the loader, could provide continuous manual effort to traverse the turret. Each man could generate approximately 50 pounds of force on the hand wheel. With proper gearing, this should have been sufficient to overcome the inertia and friction of the turret mass and rotate it slowly but steadily. The calculations were correct in theory. They failed in practice for several reasons that became apparent only under combat conditions or when the tank was examined by engineers who understood the complete system. First, the hydraulic traverse motor was not disengaged when using manual traverse. The motor remained connected to the drivetrain. This meant that manually traversing the turret required not only overcoming the turret's mass and the bearing friction, but also forcing the hydraulic motor to turn backwards, effectively making the crew pump hydraulic fluid through the system in reverse. This added tremendous resistance. Second, the turret was not perfectly balanced. The long gun barrel extended far forward of the turret ring. While there was a counterweight at the rear of the turret, the balance was imperfect. Depending on the elevation of the gun, the center of gravity shifted. When the gun was elevated, more weight was forward. This created additional rotational resistance that varied depending on gun elevation. Third, and most critically, the entire system was designed with the assumption that the engine would be running. When the engine ran, it not only powered the hydraulic system for powered traverse, but it also drove a generator that charged the batteries. These batteries powered other electrical systems in the tank. More importantly, when the engine ran, it created vibrations throughout the vehicle that actually helped overcome static friction in the turret ring bearings. The micro-movements from engine vibration kept the bearings from binding. With the engine off, the Tiger II became a very different machine. The full weight of the 11-ton turret settled onto the turret ring bearings with no vibration to ease movement. The hydraulic motor, no longer pressurized, became a significant impediment to manual rotation. The crew's ability to generate force on the handwheel became the sole source of power for traverse. American tankers discovered this limitation during technical examinations of captured Tiger IIs. The first intact Tiger II captured by American forces was taken at Grimesnil in France on August 18, 1944. Crews from the 12th Armoured Division examined it carefully. They attempted to traverse the turret manually with the engine off. 3 men working together could barely move it. The turret would shift perhaps 5 degrees with enormous effort, then the resistance would become too great, and movement would stop. A report filed by First Lieutenant William McConaughey of the 12th Armoured Division's Maintenance Section documented the problem in technical terms. He measured the force required to turn the traverse handwheel when the engine was running versus when it was off. With the engine running and the hydraulic system depressurized but not locked, 2 men could traverse the turret manually at a rate of approximately 1 degree per second. This was slow, but workable in an emergency. With the engine off completely, the same 2 men could generate movement of approximately 1 degree per 10 seconds, and only for short periods. After traversing the turret through 10 or 15 degrees, the men were exhausted and had to rest. McConaughey calculated that a full 360-degree traverse with the engine off would require approximately 1 hour of continuous manual effort by 2 strong men working in shifts, assuming they could maintain effort throughout. Implications for combat were severe. If a Tiger II's engine was damaged or killed by enemy fire, the crew lost not only mobility but also the ability to effectively engage targets that were not directly in front of them. The tank became essentially a fixed fortification with a very limited field of fire. If enemy tanks maneuvered to the flanks or rear, the Tiger crew could not traverse quickly enough to engage them. This was not a theoretical problem. It happened in combat repeatedly during the last year of the war. Tiger IIs that suffered engine damage from artillery fragments, from hits to the engine compartment, or from mechanical failure became sitting targets. Crews that attempted to continue fighting found themselves unable to track moving targets. Some crews abandoned otherwise intact tanks because without engine power, they could not fight effectively. The first major combat employment of Tiger IIs came in August 1944 during the German counter-offensive against the Allied breakout from Normandy. Heavy Panzer Battalion 503 received 45 Tiger IIs in July and August. The battalion moved to the front near Mortain to participate in Operation Lüttich, Hitler's attempt to cut off American forces that had broken through German lines. The attack began on August 7th. Tiger Eyes from 503rd Battalion advanced with supporting infantry and other armoured vehicles. The terrain was difficult, with narrow roads, thick hedgerows, and numerous small villages. The Tiger IIs, massive and heavy, struggled with the terrain. Several became stuck in narrow village streets, others through tracks when attempting to manoeuvre on soft ground. But when the Tigers did engage Allied armour, the results initially seemed to confirm German faith in the design. Tiger Eyes destroyed several American Sherman tanks at ranges exceeding 1,500 yards. American tank crews reported that their 75mm guns were ineffective against the Tiger II's frontal armour. Rounds simply bounced off without penetrating. However, American forces quickly adapted. Tank destroyers with 90mm guns moved forward to engage the Tigers. Allied fighter bombers, particularly the rocket-armed Typhoons of the Royal Air Force, attacked German armour with devastating effect. And American artillery, coordinated through forward observers with radio communications, began systematically targeting the Tigers. On August 9th, a Tiger II from 503rd Battalion commanded by Oberfeldwebel Kurt Sower engaged a column of American vehicles near the town of Barrington. Sower's tank destroyed 2 Shermans and a half-track from a hull-down position at approximately 1,200 yards. American forces called in artillery support. A barrage of 105mm shells bracketed Sower's position. One shell struck near the Tiger's engine deck. Fragments penetrated the thin armour of the engine compartment, approximately 25mm thick. The fragments severed fuel lines and damaged the Maybach engine. The engine ran rough for approximately 30 seconds, then died. Sower attempted to restart it. The starter motor cranked, but the engine would not fire. Fuel was leaking from the damaged lines. The tank was immobilized. American tanks, which had withdrawn after the initial engagement, began maneuvering to flank positions. Sower could see them through his optics, moving through the hedgerows to his left. He ordered his gunner to traverse the turret to engage. The gunner activated the electric traverse control. Nothing happened. With the engine dead, there was no electrical power and no hydraulic pressure. Sower ordered manual traverse. His gunner and loader grabbed the hand wheel and began cranking. The turret moved slowly, agonizingly slowly. The Sherman tanks were moving at perhaps 15 miles per hour, a slow advance but more than sufficient to outpace the Tiger's manual traverse. By the time Sower's crew had traversed the turret 30 degrees, the Shermans had moved out of the arc of fire and were approaching from a sharper angle. Sower made the decision to abandon the tank. He knew that within minutes, the Shermans would reach a position where they could fire into the Tiger's thinner side armour, approximately 80mm thick. At close range, even the Sherman's 75mm gun could penetrate 80mm. His crew could not traverse fast enough to engage. They evacuated the tank and withdrew on foot. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Similar incidents occurred throughout the Normandy campaign. Heavy Panzer Battalion 506, also equipped with Tiger IIs, reported multiple instances of tanks being abandoned after engine damage made them unable to effectively engage flanking enemy forces. Company Commander Hauptmann Helmut von der Esch filed a report in September 1944, noting that the manual traverse capability of the turret is insufficient when the engine is not operational. Crews cannot effectively engage targets outside a narrow frontal arc without engine power. The problem was not limited to engine damage from enemy fire. Tiger IIs suffered from chronic mechanical unreliability. The Maybach engines, stressed by the enormous weight they had to move, frequently broke down. Transmission failures were common. Final drive failures, where the gears connecting the transmission to the drive sprockets broke under load, occurred with alarming regularity. Each of these failures left the tank immobile and, critically, unable to traverse its turret effectively. By late 1944, American and British intelligence services had compiled extensive reports on the Tiger II, based on captured vehicles and interviews with prisoners. The most comprehensive analysis was conducted at the Tipeting, United States Army Ordnance Department's proving grounds in Aberdeen, Maryland, where a nearly intact Tiger II captured in Belgium was shipped for examination. The Aberdeen tests were thorough. Engineers measured every component, tested every system, and documented every characteristic of the tank. The report on turret traverse was particularly detailed. Test crews operated the tank under various conditions, with the engine running and with the engine off, with the hydraulic system functional and with it disabled. The results confirmed what frontline troops had observed. With the engine running and the hydraulic system operating normally, turret traverse was adequate. The turret could rotate 360 degrees in 19.2 seconds, slightly slower than the Sherman's 15 seconds, but acceptable for a heavy tank. The controls were smooth and responsive. The gunner could track moving targets with reasonable accuracy. With the engine running but the hydraulic system depressurized to simulate system damage, manual traverse became extremely difficult. 2 test crew members operating the handwheel continuously could manage approximately 1 degree per second, meaning a full rotation required 6 minutes of continuous exhausting effort. In combat conditions, with adrenaline, fear, and the need to also load and fire the gun, this performance would deteriorate significantly. With the engine completely off, simulating engine failure or fuel exhaustion, the turret became nearly immovable. 3 crew members working together could generate movement of approximately half a degree per second for short periods, but could not sustain this effort. The test report noted, "Manual traverse with engine stopped is impractical for combat purposes. The crew cannot maintain sufficient effort to track moving targets or to engage targets outside a narrow frontal arc." The report made specific comparisons to American tanks. The Sherman's turret could be traversed, manually, at approximately 4 degrees per second, with 2 crew members operating the hand crank. A full 360-degree rotation took approximately 90 seconds of hard work, but it was achievable, and crews trained regularly on manual traverse procedures. The Sherman's hydraulic system could be disengaged completely, removing it from the drivetrain when using manual traverse, eliminating the resistance problem that plagued the Tiger II. British reports on captured Tiger IIs reached similar conclusions. A Royal Armoured Corps technical memorandum from December 1944 stated, "The enemy Tiger II heavy tank exhibits a critical vulnerability in that turret traverse is dependent on engine operation. Crews of disabled Tiger IIs cannot effectively engage targets requiring traverse of more than 20 to 30 degrees. Flanking maneuvers are therefore highly effective against this vehicle if its engine can be disabled." These conclusions were distributed to Allied tank crews through training bulletins and tactical guidance. Tank commanders were instructed that if facing a Tiger II, the priority was to disable its mobility through track damage or engine hits, then maneuver to flanks or rear, where armor was thinner and where the Tiger's inability to traverse would prevent effective response. This became standard doctrine for engaging German heavy tanks in the final year of the war. German crews were aware of the problem. Training manuals for Tiger II crews included warnings about the limited manual traverse capability and instructions to maintain engine operation at all times when in combat or potential combat situations. Crews were told to idle the engine rather than shutting it down, even when in stationary defensive positions. This kept the hydraulic system pressurized and the electrical systems charged, ensuring the turret could traverse under power. But in the chaos of combat, these procedures often could not be followed. Artillery fire could kill an engine instantly. A lucky shot to the engine compartment could sever fuel lines or damage cooling systems. Mechanical failures happened regardless of crew care and maintenance. When the engine stopped, for whatever reason, the Tiger II's combat effectiveness dropped dramatically. The Tiger II's turret traverse limitation was a symptom of a larger problem that plagued German armoured vehicle design in the final years of the war. German engineers had pursued technical perfection and maximum capability without adequately considering the practical realities of combat and the industrial constraints of a nation losing a war of attrition. The Tiger II required extraordinary amounts of resources to produce. Each tank consumed approximately 40 tons of steel, much of it specially alloyed armor plate that required nickel, chromium, and molybdenum. These alloying elements were increasingly scarce in Germany by 1944. The optical equipment, the precision gears, complex hydraulic systems all required specialized manufacturing facilities and skilled workers. Each Tiger II took approximately 14,000 man-hours to produce, compared to approximately 10,000 man-hours for a Panther medium tank and perhaps 8,000 man-hours for a later model Panzer IV. Germany produced only 489 Tiger IIs between January 1944 and March 1945 when production ceased. This represented an enormous investment of resources for a relatively small number of vehicles. For comparison, the Soviet Union produced approximately 29,034 tanks in 1944 alone. The United States produced approximately 17,000 Sherman tanks in the same year. The strategic calculus was clear to anyone examining the numbers objectively. Germany was trading quality for quantity in an environment where quantity mattered more. A Tiger II might be able to destroy 3 or 4 Shermans before being knocked out, but if the Americans could produce 40 Shermans for every Tiger II Germany produced, the mathematics of attrition favored the Allies overwhelmingly. Moreover, the Tiger II's complexity made it difficult to maintain in field conditions. The tank required specialized tools and trained mechanics. Replacement parts were often unavailable. The final drive assemblies, which bore the tremendous stress of moving 70 tons, broke frequently and were difficult to replace in the field. Many Tiger Is were abandoned by their crews not because of combat damage, but because of mechanical failures that could not be repaired with available resources. The fuel consumption was equally problematic. The Tiger II consumed approximately 2 gallons of gasoline per mile under ideal road conditions. Cross-country consumption could reach 3 gallons per mile or more. With Germany's fuel supplies increasingly constrained by Allied bombing of synthetic fuel plants and the loss of Romanian oil fields in August 1944, operating Tiger IIs became progressively more difficult. Tanks were often abandoned simply because there was no fuel to move them. American intelligence officers who interviewed captured Tiger II crews in early 1945 noted a consistent pattern of disillusionment. The crews had been told they were receiving the finest tank in the world, a machine that would dominate any battlefield. They discovered instead that they were operating a mechanically fragile, logistically demanding vehicle that could be defeated by relatively simple tactics once its weaknesses were understood. One interview transcript, preserved in the National Archives, records the words of Unteroffizier Franz Heller, a gunner in a Tiger II from Heavy Panzer Battalion 506. Heller's tank had been abandoned near the German town of Remagen in March 1945 after the engine failed during a withdrawal. He was captured by American forces shortly afterward. "We were told the Tiger was invincible," Heller said through a translator. "We believed this. The armor was very thick, the gun was very powerful, but the tank was always breaking. The engine, the transmission, always something wrong. And if the engine stopped, we could not fight. The turret, you could not turn it. We tried, 3 men turning the wheel, but it moved so slowly. If enemy tanks came from the side, we could not shoot them. We had to abandon the tank and run." The interviewing officer asked Heller if he felt betrayed by his commanders. Heller's response was recorded, "I do not know. Perhaps they did not know. Perhaps they believed what they told us. But I know that I would rather have had 3 Panzer IVs than 1 Tiger. The Panzer IV, it was reliable. It moved when you needed it to move. The turret turned. You could fight with it." This sentiment was echoed by other captured Tiger II crewmen. The tank's theoretical superiority meant nothing when it could not be maintained, when it consumed fuel that was not available, when mechanical failures left it immobile on the battlefield. The complex hydraulic turret traverse system, designed to give the crew easy control of the massive turret, became a critical vulnerability when the system depended absolutely on engine power. The Tiger II was not an isolated example of German engineering philosophy producing impractical vehicles. The same pattern appeared across multiple weapons systems in the final years of the war. The Panther tank, while more successful than the Tiger II, suffered from chronic final drive problems and engine fires. The Ferdinand and Elephant tank destroyers were mechanically unreliable and lacked defensive machine guns, making them vulnerable to infantry attack. The Maus super heavy tank, weighing 188 tons, was so impractical that only 2 prototypes were completed before the project was abandoned. This pattern reflected fundamental misunderstandings about industrial warfare. German military leadership and many German engineers believed that technological superiority could compensate for numerical inferiority. They designed weapons that were theoretically superior to anything the Allies produced. But these weapons often could not be produced in sufficient numbers, could not be adequately supplied, and could not be maintained under field conditions. The Allies, particularly the Americans, took a different approach. The Sherman tank was not technologically superior to German heavy tanks. Its 75mm gun could not penetrate a Tiger II's frontal armor. Its own armor was vulnerable to German tank guns at most combat ranges. But the Sherman was reliable, easy to maintain, simple to operate, and produced in overwhelming numbers. More importantly, it was designed as part of a complete system that included logistics, maintenance, crew training, and tactical doctrine. American tank doctrine emphasized combined arms operations. Shermans operated with infantry support, artillery support, air support, and tank destroyer support. When a Sherman encountered a Tiger II, the response was not to engage in a one-on-one duel. The response was to call in artillery, to maneuver for flanking shots, to bring up tank destroyers with more powerful guns, to coordinate with other Shermans to attack from multiple directions simultaneously. The system compensated for individual vehicle limitations. German doctrine, by contrast, increasingly relied on the theoretical superiority of individual weapons systems. Tigers were expected to dominate through their own capabilities. When those capabilities proved insufficient, or when the weapons failed mechanically, there was often no backup system, no alternative approach. Crews trained on Tigers had limited experience with combined arms coordination because the doctrine assumed Tigers would not need such support. The Tiger II's turret traverse problem exemplified this philosophical difference. German engineers had created a sophisticated hydraulic system that worked well under ideal conditions. But they had not adequately considered what would happen when conditions were not ideal, when the engine was damaged, when hydraulic lines were severed, when the electrical system failed. The manual backup system was inadequate, apparently designed more to satisfy a requirement on paper than to provide genuine combat capability. American engineers, by contrast, designed the Sherman's turret traverse with the assumption that systems would fail. The hydraulic traverse could be completely disengaged from the manual system. The gear ratios for manual traverse were calculated to allow effective operation by 2 crew members without requiring superhuman effort. The system was redundant, practical, and designed for the messy reality of combat rather than for theoretical perfection. This difference in design philosophy extended beyond turret, traverse to every aspect of tank design. The Sherman's engine was a commercially available design, either the Continental radial gasoline engine or the General Motors diesel, both proven in commercial use before the war. Parts were readily available. Mechanics were familiar with the engines from civilian experience. The Tiger II's Maybach engine was a specialized design, requiring specialized parts and specialized maintenance knowledge. The Sherman's transmission was a synchromesh design adapted from heavy truck transmissions. It was reliable and relatively easy to repair. The Tiger II's Maybach transmission was a complex, specialized design that required precise tolerances and frequent maintenance. The Sherman's tracks lasted approximately 2,500 miles under normal conditions. The Tiger II's tracks lasted perhaps 1,000 miles before requiring replacement, and replacement tracks were often unavailable. In every comparison, the pattern repeated. The German design was theoretically superior but practically problematic. The American design was practically effective even if theoretically less impressive. And in a war of attrition, practical effectiveness mattered far more than theoretical capability. By the spring of 1945, when the war in Europe entered its final weeks, the strategic failure of German armoured vehicle philosophy was undeniable. Germany had produced approximately 47,000 tanks and assault guns of all types during the entire war. The Soviet Union had produced over 100,000 tanks. The United States had produced approximately 88,000 tanks and tank destroyers. Britain had produced approximately 28,000 tanks. The combined Allied production was more than 5 times German production. Those 3 American tankers standing in front of the abandoned Tiger II outside Mons in May 1945 had discovered something more significant than a mechanical limitation. They had discovered the physical evidence of a failed philosophy, a tangible demonstration of how brilliant engineering could produce failure when divorced from practical reality. The Tiger II represented the endpoint of a design philosophy that valued individual perfection over systemic effectiveness. Every component was engineered to the highest possible standard. The armour was the thickest that could be mounted on a mobile vehicle. The gun was the most powerful that could fit in a tank turret. The optics were the finest in the world. The hydraulic systems were sophisticated and, under ideal conditions, highly effective. But the tank, as a complete system, was less than the sum of its parts. The thick armour made the vehicle so heavy that the engine and transmission were constantly stressed beyond their design limits. The powerful gun required massive amounts of ammunition, each round weighing over 40 pounds, limiting the number of rounds that could be carried. The sophisticated hydraulic systems created dependencies that became critical vulnerabilities when components failed. The entire design assumed conditions that rarely existed in actual combat. When Sergeant Early and his crew tried to manually traverse that turret and found they could barely move it, they understood something that German engineers had apparently not fully considered. A tank turret that cannot traverse is not a tank, it is a fixed fortification with a limited field of fire, and a tank that becomes a fixed fortification when its engine stops is not a reliable weapons system. It is a liability, a collection of valuable resources that will likely be abandoned when mechanical problems occur or when enemy action disables the engine. The reports filed by American technical intelligence officers were read by tank designers and military planners. The lessons influenced post-war American tank design. The M26 Pershing heavy tank, which entered service in the final months of the war, had powered turret traverse, but also had an effective manual traverse system that could be operated independently of the engine. The M46 and M48 tanks that followed in the late 1940s continued this philosophy. Redundancy, reliability, and practical effectiveness took precedence over theoretical maximum performance. For the German tank crews who had served in Tiger IIs during the final year of the war, the experience left lasting impressions. Those who survived and were interviewed years later spoke of the strange mixture of emotions they felt about the vehicles. Pride in operating what was theoretically the most powerful tank in the world. Frustration at the constant mechanical problems. Fear when the engine stopped and they realized they could not effectively fight. Anger at commanders who had sent them into battle in machines that promised more than they could deliver. One former Tiger II commander, interviewed by a military historian in the 1970s, recalled the moment when his tank's engine was disabled by artillery fire during a battle in eastern Germany in March 1945. Soviet 34 tanks were advancing toward his position. He ordered manual traverse to engage them. His crew strained at the handwheel. The turret moved perhaps 10 degrees. The 34s were moving at 20 miles per hour, angling for his flank. He knew he could not traverse fast enough to engage them. He gave the order to abandon the tank. "We ran," he said. "We left that enormous machine sitting there, useless. The gun was operational. We had ammunition. The optics were perfect, but we could not point the gun at the enemy, so we ran. I remember thinking as I ran that someone in Berlin had decided this tank needed the biggest gun, the thickest armor, the best optics, but no one had decided that the tank needed to be able to fight when the engine stopped. That decision, that oversight, cost us the tank. It cost many crews and their lives. The abandoned Tiger IIs, scattered across Europe in the spring of 1945, told a story about the nature of technological warfare. They demonstrated that sophistication without reliability is not an advantage. They showed that theoretical perfection means nothing if practical limitations prevent effective use. They proved that in industrial warfare, the ability to produce adequate weapons in large numbers matters more than the ability to produce perfect weapons in small numbers. The Tiger II, with its 11-ton turret that could barely turn when the engine was silent, became a symbol of a larger failure. It represented a military and industrial establishment that had pursued excellence in individual components while losing sight of the broader requirements of sustained warfare. It showed what happened when engineers designed for ideal conditions rather than for the chaos and breakdown that characterized actual combat. Those American tankers examining the abandoned Tiger II were looking at more than a disabled vehicle. They were looking at the physical manifestation of a strategic miscalculation, a tangible example of how a nation could pour enormous resources into weapons systems that ultimately failed not because the engineering was poor, but because the engineering solved the wrong problems. The Tiger II was a magnificent machine in many ways, but it was a magnificent machine that could not turn its turret when its engine stopped. And that single limitation, that one dependency on engine power for a system that needed to function independently, made all the magnificence irrelevant. The tank that was supposed to dominate every battlefield became instead a cautionary tale about the difference between theoretical superiority and practical effectiveness. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.